Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. This video is going to be an extension of my last video, and it's going to be about properties of exponents and radicals. If you watched my last video, you'll know that radicals can be changed to exponent form. So these rules actually really apply in very similar manners. Anytime you get stuck, just put it in the other format so that your brain likes it better and work from it there. Before we get too deep into this, we're going to go back into maybe some things that you learned in junior high. So let's look at, say, x to the fourth being multiplied by x to the third. I always told my junior high students that if they were ever worried about what the answer was, that when in doubt, write it out. So we have x, 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 x. They're all being multiplied together. So the simpler way of saying this is that it is x to the seventh. Okay. What about 4 to the fourth times 4 to the third? What do you think that is? And I want you to really think about it. If you need to, write it down. Don't lie to yourself. Let's see what you thought. Compare it to what really happened here. We have 4 times 4 times 4 times 4. And then that's being multiplied by 4 times 4 times 4. Ah, there are 7 4s there. So this is 4 to the 7th. You might find you or one of your friends has mistakenly made that base 16. We don't have 7 16s, we have 7 4s. So make sure that when you're adding your powers, you're keeping your base the same. All right, so x to the 8th divided by x to the 3rd. Okay, so when in doubt, write it out. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. We can take 3 away from each. We have 5 left in the top. Why in the top? Because the top had more. So when I'm doing this, I always put my answer with where it has more. So equals x to the 5th. Okay, so here, when we multiplied bases, we added the exponents. And when we subtracted bases, not subtracted, I've got my brain messed up. When we divided bases, we subtracted the exponents. Okay, so a couple other things we're going to look at here, keeping in line with that. X to the 5th divided by x to the 5th. Well, if we're going with the divided, you subtract exponents. 5 minus 5 is 0. But we also know anything divided by itself is 1, which is why anything to the 0 power is 1. All right. And now let's think of a to the 3rd divided by a to the 9th. Well, we subtract, and 3 minus 9 is negative 6. Or let's think about it, that whole when in doubt, write it out. A, 1, 2, 3, 4, 5, 6, 7, 8, 9. Cancel 3, cancel 3. There's always a coefficient of 1, so you can't take that away. So 1 over a to the 6th. So you could say, okay, who has more, the top or the bottom? How many more do they have? The bottom has 6 more. But this highlights the fact that a negative exponent works like this. I have a lot of students that tell me, we never work with negative exponents. It's just not something we do. And then I remind them. They see scientific notation a lot. And they're like, oh, you moved the decimal 3 spots to the left. Why are we moving the decimal smaller? It's because we're dividing by 10. So you're really doing 4.2 divided by 10 3 times. So you have been doing negative exponents more than you think. However, you may or not recognize that you're doing it. So this is just kind of a quick synopsis of reminding you of stuff. There's one more I need to remind you of. Actually, two more. What happens when you have x to the 4th cubed? Okay, let's think. When in doubt, write it out. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. We have 12 x's. So this is x to the 12th. So when you have double powers on one base, you multiply. And I find some students confused. When do I add? When do I multiply? If you're confusing it, when in doubt, write it out. Okay. What about one last one, then we'll get into what this is really supposed to be about. What about this one? Think about it. Now I'm going to, when in doubt, write it out. Here's the first one. 4x, x, x, y, 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 y. All right, when I look at that, I see a 4 and a 4 here, so that's 16, or 4 squared. 1, 2, 3, 4, 5, 6, x to the 6th. And 1, 2, 3, 4, 5, 6, 7, 8, y to the 8th. So this squared has to happen to the coefficient as well as the variables. And it was technically, they all had double powers, so that's a monomial, and you can do that. Just a reminder, if you have a binomial, you must, quote unquote, FOIL it out. Even if you have a third power or a fourth power or a fifth power, you have to, quote unquote, FOIL it out. In fact, I have an entire video dedicated to binomials to a power and using Pascal's triangle. This is a monomial because there's no plus or minus signs. So the rules work different here than they do here. So please, please, please keep that in mind. Okay, so how do these work and what can we do? Well, 25 to the 5/6 times 25 to the negative 1/3. The bases are the same, so we can add the exponents. So you can grab a calculator if you don't like doing this, or we can make them a common denominator. 25 to the 5/6 times 25 to the negative 2/6. Did that help? Negative 1/3 and negative 2/6, same thing. When you multiply bases, you add your exponents. That gives us 25 to the 1/2 power. There's two ways to finish and simplify this from here. You can either go, oh, the 1/2 power. That's an index of 2 with a power of 1. In my last video, I showed how radical form and exponential form translate. And I'm sure you know that the square root of 25 is 5. Or you could say, hey, 25 is 5 squared. And we're doing that to the 1/2 power. And with double powers, you multiply, and 2 times 1/2 is 5. So we can use radicals and rational exponents interchangeably so that they work together. Okay. So keeping in mind our power rules, let's think about what it would be if I had 5 times a to the 1/3 times ab to the 4/5. And that's going to be raised to the 2/3 power. So remember order of operations, your PEMDAS, parentheses, exponents, multiply, divide, add, subtract. And if you haven't seen any of my other videos, Dividing is multiplying. Subtracting is adding. Dividing by 2 is the same as multiplying by 1/2. Subtracting 5 is the same as adding -5. So that's why I write PEMDAS a little different. So we're supposed to take care of our parentheses first. Okay? Our parentheses have double powers, and double powers are supposed to be multiplied. So we'll have 5, a to the 1/3. Now technically there's a 1 here. So 1 times 2/3 is 2/3. And 4/5 times 2/3, multiply the top, multiply the bottom, right? b to the 8/15. So now I can take care of my exponents. Since I have common bases, I can add those powers. 5 2/3 and 1/3 add to a whole, so I don't have to write anything down. And I'll have b to the 8/15. It is perfectly acceptable to leave your answer like that. If it says write your answer in a radical form, 5a, the 15th root of b to the 8th. These mean the exact same thing. I am not going to be picky in my classroom on which way you write it unless the directions specifically state one way over the other. Okay, let's do the third root of x to the 7th y squared over 125x. I will not say I always do what we're about to do. Here's a step first because I've come across a lot of problems and I've gotten creative in the way that I work with them. But if you can reduce the fraction under a radical, a lot of times it is best to do that as your first step. It's not always, it's not a hard and fast rule, because sometimes you might reduce it and then just have to unreduce it, which I'll talk about why here in a minute. But in this case, it is best to go ahead and reduce the radical first, because there's an x in the denominator, 7x's in the numerator. We can use our subtracting of powers and come up with the third root of x to the 6th, y to the 2nd, over 125. So if you're a when in doubt, write it out kind of person, this time I'm going to go ahead and write it out. 1, 2, 3, 4, 5, 6, 1, 2, and 125 is 5 times 5 times 5. Okay, our index is 3. We're circling groups of 3. So here's this in the numerator, and this in the numerator, and this in the denominator. So our final answer will be x squared, the third root of y squared, because they didn't have partners. They were left over in the sock, or in the basket when we folded socks, and a group of 5s on the bottom. I don't need to worry about absolute values because this is an odd index. Okay, so because of history and what numbers were in the book of radicals, we're going to do stuff because they did it back that way before calculators, and we get to still do it that same way. But here's why. 1 divided by square root of 2. Okay, this would be 1 divided by 1.414 blah, 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 blah. Okay, well, when's the last time you did this by hand? Just even stopping at that decimal, we've got to move this over 3 places. There we go. How many times does 1,414 go into 1,000? 0 times. Put down the decimal, add a 0. Now it's how many times does 1,414 go into 10,000? I don't know about you, but that is not a problem that I do very quickly without a calculator. Okay. What about this problem? Okay, the square root of 2 is that 1.41, so this would be 1.414 divided by 2. Well, hey, I can do that pretty quickly because 14 cut in half is 7, right? Divide by 2, 7, 14, 0, bring down the 1, 0, bring down the 4, 7. It's about 0.707. I was even able to show the work. And the reason because it's about 0.707 is this technically still goes on. So this I was able to do quickly and easily, whereas this one I was not. Why am I comparing these? Well, if I multiply by this numerator and denominator, that would give me the square root of 2 for the numerator and the square root of 2 squared for the denominator. And the square and the square root are inverse operations, so they cancel out, which is the square root of 2 over 2. They are equivalent problems, just written in different formats. So for this reason, your denominator must be an integer. Your variables need whole number exponents. So your equation is not reduced until this happens every single time. Again, why do we do it? It's because of history, but it has to happen every single time. Integers and whole number exponents. So what's that going to look like? So right now we have the 5th root of 27y squared. Our denominator cannot be part of this radical because a radical can only have integers in it. It can have variables as well, but it all has to be in the numerator. We can't have a ratio in it. So no ratios inside radicals. So that's a problem right off the get-go. So the first thing we're going to do is we're going to split this up. We're going to have the 5th root of 7 in the top and the 5th root, and I'm going to write this out. 27 is 3 times 3 times 3 times y times y. Okay, so we have to perfect this denominator, so we're going to need to multiply it by the 5th root of something. Whatever we do at the bottom, we have to do the top. So that when we put these two baskets together, it works out perfectly to perfect groups of 5. So I have a 3, 3, and 3. So I'm going to need 2 more 3s to make that group of 5. And then I have y, y. I'll need 3 more y's. So whatever I do to the bottom, I must do to the top. All right, so dump those baskets together. We now have the 5th root. I'm not actually going to multiply it. I'm just going to leave it in factored form of 3 times 3 times 7 times y times y times y in the numerator. And the 5th root of 3 times 3 times 3 times 3 times 3 times y times y times y times y times y. And now we can see when we fold socks, I'm not sure what kind of animal has 5 legs, but whatever. Fold the socks here, a group of 5. Fold the socks here, group of 5. The denominator, or the basket in the basement, must work out perfectly, and it does. We had a group of 3s, and we had a group of y's. No absolute value signs needed because that is an odd index. In the top, there's no folding that can be going on in the upstairs rooms. So we're just going to have to leave everything in the basket. So we have the 5th root of 9 times 7 is 63, y to the 3rd. Now, I know 63 divides by 3. I get that. But 63 is stuck inside the basket. And this 3 is outside the basket. So you cannot do anything with stuff inside the basket versus stuff outside of the basket when it comes to reducing. This is our final answer. I'm going to write the next one a little bit differently. The third root of 4 over 81. I'm going to leave everything in the single basket and just complete it as much as I need to. So I know 4 is 2 times 2. And I know 81 is 9 times 9, and those are each 3 times 3, so it's 4 3s. Starting off good, I have a perfect group of 3s, but then I still would have a 3 left in the denominator, and I can't do that. So I'm going to multiply by 3. Still not perfect, so another 3. Now that's perfect. So I have 2 pairs of 3s in the bottom that can go outside. And in the top, I can't fold any socks, so everything's underneath the radical. So when I multiply that together, that's 36. And when I do 3 squared, I get 9. Again, the 36 is inside the radical, the 9 is outside the radical, so that's my final answer. So that is reducing radicals. Make sure that your denominator is always the same. If you notice, all of our radicals so far have been a monomial. So working with binomials changes everything. So remember, if you have a plus or minus sign, it changes up what you're doing. Okay, so here we have a subtraction problem. And right now we can't do anything. They're not like terms because they're not like radicals. But none of our radicals are reduced, so it's kind of like 3 problems, actually 4 problems in one. So the first thing we're going to do is we know 20 is 4 times 5, which is 2 times 2. And some of you can do this without doing the next step. I understand you can kind of jump lines. But we have a 2 times 2 times 5, which is a pair of 2's with 5 left over. Okay, 600 is 6 times 100. 6 is 2 times 3. 10 times 10. 2 and 5. 2 and 5. So 1, 2, 3 2's. A 3 and 2 5's. So a pair of 5's and a pair of 2's. So that would be 10 with 6 left over. And 45 is 9 times 3, 9 times 5, sorry. 3 times 3. So we have 3 times 3 times 5, so a pair of 3's with 5 left over. So I just folded socks with each term. Now, I'm going to rewrite this. I'm going to do a little extra step, and then I'm going to explain it and show it something similar. Okay, so if I reorder this and I write 2 squares of 5 minus 3 squares of 5 minus 10 squares of 6. These two have a common factor of the square root of 5. And if I factor that out to the front, I'm left with 2 minus 3, which is negative 1. And the square root of 5 times negative 1 is negative 1 square root of 5. And again, I was just talking about these terms. And I would still have minus 10 root 6, minus 10 root 6, minus 10 root 6, because I didn't do anything with it. Do you remember when you'd have like 2x minus 10y minus 3x, how you would call these like terms? And you'd say 2x minus 3x is negative 1x. That's really what we're doing here. 2 root 5 minus 3 root 5 is negative 1 root 5 minus 10 root 6. We're combining like terms still. Why can we do that? Technically, it's because of factoring, but I just wanted to make sure that you knew that it was related to like terms. Okay. I know this is a commonly asked question, so I do want to go ahead and state something really quickly. I've had students ask, What if I had the third root of 7 times the fourth root of 2? Or not of 2, of 7. The third root of 7 times the fourth root of 7. Can I do them? And the answer is yes, but not in this format. You must first think of these as powers. 7 to the 1/3 times 7 to the 1/4. Now that it's written as exponents, we can add the fractions. Because when you're multiplying bases, you add exponents. So I'm going to rewrite this to they have a common base, or common denominator. And now we can add 4/12 and 3/12. Or the 12th root of 7 to the 7th power. Could I have unreduced these here? If this is 1/3, isn't that the same as, see this 4/12 right there? Absolutely. You can do it that way, because this is a power of 1, this is a power of 1. Can you multiply these both by 4 and get 12 and 4? Yes. Can you multiply these both by 3 and get 12 and 3? Absolutely. It's because of that fraction relationship and using equivalent fractions. So definitely you can do that, as long as they have the same base. That's a big part. Okay? Okay, so this problem looks like a distribution problem because it is. So the first thing we have to do is we have to take these two and multiply them together. So we're taking the 2 and we're multiplying it by the third root of 5. Okay, nothing we can do there. Minus, then we're taking that third root of 25 and we're multiplying it by the third root of 5. Now, those are both baskets. We can dump those baskets together because they're both the third root. So we have the 2, third root of 5 minus the third root. I'm going to remind you, 25 is 5 times 5. So we're going to have the 5 times 5 from the 25, and then we're going to have the times 5 from here. So technically we have a group of 5s. So my final answer is the 2 times the third root of 5 minus 5. I have a prime number underneath my radical, so I know I can't reduce that. Okay, so here we see a binomial being multiplied by a nomial. I know it's multiplied because there's nothing in between. So how can I do this? I'm going to go back and use my grid work. I like to use grids whenever I'm multiplying binomials. That way I can keep everything nice and organized. I don't care which one goes on top. 5 plus root 2. 5 minus root 2. So I'm going to write in pencil what we're multiplying in each spot. Here we're multiplying 5 times 5. Here we're doing 5 times the radical 2. Here we're doing 5 times negative radical 2. And here we're doing negative radical 2 times positive radical 2. Okay. So 5 times 5 is 25. 5 times the square root of 2 is just 5 square roots of 2. Now keep in mind a positive times a negative is a negative, and then we're multiplying 5 square roots of 2. A negative times a negative is a negative times a positive is a negative. And we have the square root of 2 twice. Okay, keep in mind that a square and a square root are inverse operations, so they cancel out. So we have 25 minus 2. which is 23. And then see how this is minus 5 root 2 and this is plus 5 root 2? They also cancel each other out. And so the answer is just 23. Why did we get such a simple answer? Well, if you notice, this is that a plus b, a minus b pattern, which is equivalent to a squared minus b squared, because the middle will cancel out every time you FOIL these together. So 5 squared is 25, minus, if you take the square root of 2 and you square it, you get 2. And 25 minus 2 is 23. It's just a nice thing because these are conjugates. And if you watched my complex numbers video, you would have seen me talk about conjugates in that video as well. So I've done adding, subtracting, multiplying, but I haven't done dividing of rational problems, right? Except for when it was a monomial. So what happens when you have this? And the big thing is this is a binomial. I'm going to do these side by side because I want you to see the difference. Okay. When it's a monomial, I can multiply this by the square root of 3 so that the top becomes 5 square roots of 3 and the denominator becomes 2 times the square root of 3 squared, which is really just 3, and 2 times 3 is 6. If I were to just multiply the denominator by the square root of 3, it would become 2 square roots of 3 minus the square root of 3 squared. I still have a radical in the denominator. Boo. We don't want that. So the only way to make the denominator rational, or rationalize the denominator, is to take advantage of that conjugate pattern. So instead of multiplying just by another monomial, since this is a binomial, I need to multiply by a binomial. Notice how I changed the sign. Okay, so in the numerator, I need to distribute. That would give me 10 plus 5 root 3. And if I were to FOIL out the denominator, I would 4 plus 2 root 3 minus 2 root 3 minus the square root of 3 squared. So 10 plus 5 square roots of 3 over 4 minus 3, which is 1. Oh, so this one happened to work out to something quite simple, 10 plus 5 square roots of 3. So remember, when you do these and you have a binomial in the denominator, you need to multiply by a binomial to fix it. If you have a monomial in the bottom, or the denominator, you need to multiply by a monomial to fix it. Please, please, please keep that in mind. Also, one other thing to keep in mind. Let's say you wound up with an answer of 4 plus 3 root 5 over negative 7. I would prefer, personally, that you didn't leave this in this form. I would multiply the top and bottom by negative 1. That way I get negative 4 minus 3 root 5 all over positive 7. If you'll notice, I just flip-flopped all the signs. It's preferred by most mathematicians that I know of to have a positive denominator. It's not necessarily mandated, but it is kind of the practice. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.